We're going to be talking about density. We're going to start by just talking about different aspects of density. There's a lab that you did, and we're going to end with some calculations. So density is defined as mass per unit volume. This is something that I'm sure you've learned about in previous science classes in high school or even middle school. Density is an intensive property. So what that means, and you may have learned that in the past or you may have not learned that in the past, intensive properties are properties that do not depend on the amount of substance that you have. It's the same regardless of how much sample is present. So for example, if you have a swimming pool full of water, it has a density of 1 gram per mil. If you have a cup full of water that you're drinking out of the tap, then it has a density of 1 gram per mil. It doesn't matter if you have a swimming pool sized sample or a glass sized sample or a drop of water. It has the same density regardless. The opposite of this would be an extensive property, which does depend on the amount. So for example, mass is an extensive property, where if you have a swimming pool full of water, then you have a much larger mass than if you just had a glass full of water or a drop of water. Shown in table 0.4 are densities of some common materials. Water is shown there with a density of 1.0000 gram per cubic centimeter. That is at a specific temperature, 3.98 degrees Celsius. The density of most substances varies with the temperature. Now, water is interesting because water is often used as a measure of relative density. And so what I mean by that is that you might choose to put something in water to see if it floats or sinks. And if it sinks, that means that that substance is more dense than water. And if it floats, that means it is less dense than water. As I just said, density does vary with temperature. For most substances, the density of water is 1 at a temperature of about 4 degrees, but that is sort of its maximum density. Now, this is an example of relative density. And so Coke with full sugar contains 355 grams of water, 39 grams of sugar, with a total mass of 394 grams. Diet Coke contains less mass because the mass of the artificial sweetener, it doesn't need the same mass of artificial sweetener in order to generate the same amount of sweetness, right? The amount of sweetness is determined by the sweet receptors in your taste buds. And so generally, artificial sweeteners have a much more intensely sweet flavor, sweet taste, and so you don't need the same amount as sugar. Therefore, the total mass is much less, and since both have the same volume, regular Coke ends up being slightly more than 1 gram per mil, and diet sodas and Diet Coke tend to have a density that is slightly below 1 gram per mil. We're going to do a couple of density calculations just to make sure everybody knows how to do these. I would suggest that you practice these because regardless of how many times you've learned them, they tend to confuse people. So we're going to do some density calculations, and then we'll do a couple of unit conversions that include density in a few minutes. So at the end of that density intro, we had a couple of calculations. The first one, a block of an unknown metal with dimensions 3 by 2 by 1.5 centimeters has a mass of 102 grams. What is the likely identity of the metal? Now this is a common way of using density. You might use density to determine the identity of an unknown substance. So we have a table down here at the bottom that includes densities of some common metals. And by comparison, water is in here as well. And so what we need to do is we need to calculate the density based on the numbers that were given and compare that to the numbers in the table. So there are a lot of values, a lot of units given in the table. And so I see cubic centimeters. If I multiply these three together, we'll get cubic centimeters, and grams is in the numerator, so I can just use the numbers I'm given and use this first column here for comparison. The denominator, the numerator is going to be mass, so that's this 102.0 grams, and the denominator is going to be cubic centimeters. If you ever forget the formula for density, if you just use the units that are given, that tells you the formula. Mass is in the numerator, Cubic centimeters is in the denominator. So that means we need to multiply length times width times height. So this is my block of metal. We're going to multiply those three numbers together to get the volume. Density is mass divided by volume. That weird looking P is a nu. The volume is what we're calculating here. Volume is length times width times height. When you multiply those three things together, then you're going to get 9. Each of them has units of centimeters, which means that the volume is in units of cubic centimeters, which means my density is 102.0 grams divided by 9.0 cubic centimeters, which gives me 11.333333 forever grams per cubic centimeter. And if I compare that to the numbers in the table, it appears that the closest one is lead, 11.36. So my answer in this case is just the word lead, right? If this were a calculation problem, then I would have to worry about significant digits, but it isn't. All I need to do is write lead, along with, of course, I need to show my work, because if I don't show my work, then my teacher doesn't have any idea that I know what I'm doing. So just the word lead without any work would, of course, be worth nothing. Well, maybe 1 point, but not very much. So you should probably show your work. It's a good idea. If we move on to the second problem, what is the mass in grams of 497 microliters of mercury? Mercury's information is given down here. And we have density is mass divided by volume. If we rearrange that algebraically, we can get the mass that we're looking for is equal to density times volume. So that means that we simply need to take the density, multiply by the volume, but none of our volumes, none of our densities are given in microliters, and so we have to convert from microliters to milliliters. So you can see that the density of 13.55 grams per cubic centimeter, that's the same thing as grams per milliliter. So 1 milliliter is the same as 1 cc, which is 1 cubic centimeter. So we need to convert microliters into milliliters. 497 microliters. There are 1,000 microliters in a milliliter. I don't know if you remember that or not, but you can always convert microliters to liters and then convert liters back to milliliters. That works the same way. But microliters and milliliters are different by a factor of 1,000. If you're a biology major, you should probably learn that anyway. You can also, if you're dividing by 1,000, you can simply move the decimal over 3 decimal points. So if I multiply by 0.497 milliliters, multiply the density times that volume, that gives me 6.73435 grams. And of course I need to round to the right number of significant digits. It appears that 13.55 has 4 sig figs, 0.497 has 3 sig figs, which means my answer needs to have 3 sig figs. So 6.73 grams is my answer. The last thing I wanted to show you was how you would convert between units. Now, not all of these are density conversions, but I wanted to introduce density before we discussed interconverting units, because density is at the end of these unit conversions. So we're going to do some examples. We're going to perform the following conversions. This is the way it'll look if I give you a problem like this. You should anticipate one of these on your next quiz or homework, and certainly on your exam. So A, we're going to convert 9.87 times 10 to the minus 8 microseconds into femtoseconds. That's going to require that we remember our prefixes. These are the prefixes that you need to remember. Micro is here, so we're going to, if we convert from microseconds to seconds, then we can convert from seconds to femtoseconds. So this is our conversion from microseconds to seconds. Microseconds goes on the bottom so that it cancels, and then femtoseconds goes on the top so that seconds cancels, and that gives us units of femtoseconds, so we have 9.87 or 98.7 femtoseconds, or 9.87 times 10 to the first. Now, at the end of these calculations, you should always make sure that the number matches the units, okay? So what I mean by that is that a femtosecond is tiny. That's like a super fast, super small unit of time. And a microsecond might seem pretty short time as well. But a femtosecond is much, much faster, much shorter time frame than a microsecond. So the numbers should get bigger because the units are smaller. Okay, so you should kind of verify that when you do a calculation. Another way to think about this problem is, if you can remember here from our unit conversion, if you can remember that a microsecond is 10 to the minus 6 seconds and that a femtosecond is 10 to the minus 15 seconds, you can just compare microsecond to a femtosecond. They're different by 8 orders of magnitude, right? 9 orders of magnitude. 15 minus 6 is 9. So if we go all the way down, there is 10 to the 9 femtoseconds in 1 microsecond. Okay, so that's a difference of 10 to the minus 15 comparing 10 to the minus 6. So another way to do this is to do a direct unit conversion where 1 microsecond contains 1 times 10 to the 9 femtoseconds. Microseconds cancels, and now you've done it in one step. If this confuses you, though, I would suggest that you go to the base unit and then go back. Okay, you should get the same answer, though. That's up to you. Let's do B, 14.4 pounds per square inch. That is a unit of force. And we're going to convert that into milligrams per square centimeter. So we're going to think about what we know. We know 1 pound is the same as 453.592 grams, or 1 kilogram is the same as 2.205 pounds. We also know that 1 inch is 2.54 centimeters. So we're converting English units into metric units, and you just have to convert them one at a time. So convert the numerator first, or the denominator first, and then convert the other. So we're going to start with pounds. We're going to go from pounds to grams because that's a more direct conversion. So pounds is on the bottom in our conversion so that it cancels. And then now if we stop here, we'll have units of grams per square inch. But we're not done yet because we need to convert the denominator into square centimeters. Oh wait, we need to go to milligrams. Sorry, forgot. So we're going to go from grams to milligrams. Now we're going to convert the denominator into square centimeters. Remember that if you square the unit, you also must square the number, which means that it's 2.54 squared square centimeters in 1 square inch. And now we have units of milligrams per square centimeter. So we're done once we do this calculation. We get 1.012419 times 10 to the 6th. Now we're concerned about significant digits. So 14.4 has 3 sig figs. 453.592 has 6. The number 1,000 is exact in 1,000 milligrams per gram. 2.54 is exact. That means that our answer in the end needs to have 3 significant figures to match the 14.4, which means 1.01 times 10 to the 6th milligrams per square centimeter. Our last calculation, part C, again has a numerator and a denominator. This is a density, grams per mil. We're going to write down what we know about grams if we want to go from grams to pounds. And then, of course, if we want to go from milliliters to cubic inches, we need all of this information. So we're going to start with grams to pounds. We're going to put 453.592 grams on the bottom so that it cancels. 1 pound on the top. Grams cancel. Now we're going to convert milliliters. Remember, this is the same as cubic centimeters. And then we can convert that into cubic inches. I have here a conversion here that 1 milliliter is the same as 1 cubic centimeter. I would suggest that you include that just so that you don't lose track of your conversions. You don't necessarily have to show me that conversion, but I think you might get confused if you don't include it. And then of course 2.54 cubed cubic centimeters in 1 cubic inch. So we have cubic centimeters on the top here so that it cancels, and then we end up with pounds per cubic inch, and that's what we're looking for. So if we write down the number, it's 307.190614, 5 lots of sig figs. Now if we label everything with the number of significant figures, 8.503 has 4, 453.592 has 6. These numbers are exact. 2.54, these numbers are all exact, so they are infinite in sig figs, and so that means we need to round to 4. So this number needs to be rounded to this place here, the 1, and then that 9 is going to round up, so we're going to get 307.2. Don't forget units, pounds per cubic inch. And that is our final answer.